In this video, I'm going to show you how you can train a model for image classification. So first of all, let's have a look at the data. So if I open what I downloaded from GitHub, like this folder. So in Colab, there are all the notebooks that you can use if you use Colab. We are going to use the installation on local computer, so it's in local. In local, there's something called classification, and if you go in data sets, then you have two folders, one for test, which has two different images that will use for testing our classification. Here's it. We go to adenocarcinoma normal. We have two different folders, one for training and one for validation. So if we go into training, we have images for normal tissue and for adenocarcinoma. For example, this is an image of HNs in tissue for a normal patient. And if I use this one, this is for adenocarcinoma. So first of all, don't look the sign, and if you're a pathologist, you can tell that this is normal tissue, this is adenocarcinoma. Second main difference is that this one is much larger. It's 2048 times 1536 pixels, while this one is just 512 by 512. Now, this is because the data I got this images from, there are many more examples of adenocarcinoma images than normal images. And so as we want to get a balanced set of classes, one way to get there is to crop the images from normal tissue into smaller images. So we have roughly the same number of images for normal tissue and adenocarcinoma tissue. Of course, the total amount of data is larger with adenocarcinoma tissue, but at least when we train with as many examples for one class than for the other. How does the algorithm know which class the images are from? If you scroll down, there's a file which is called, so you see the staining is really different from one image to the others. This is much more bluish. And so if you scroll down, you're going to find a file which is called labels.csv. I open it. Then, so here you have two columns. One which corresponds to the name of the image, and then second to the class. So here all the first images correspond to class 0 and second one for the two classes, normal and adenocarcinoma. All right? We're going to start by training architecture. So very simple architecture for image classification. So if we want to open the training notebook, we first need to activate virtual environment. We type in conda activate, and then the name of the environment, which is workshop. Now you see the beginning of my line, there's workshop on, so I know that I'm inside virtual environment. Then the easiest way to then launch a notebook is to go directly to the right location where my files are. So this is where everything is. So if I do shift and right click, then there's something which is called copy as path. So then, if I want to see the path, we can just do Control D, and I see that this folder is in my D drive, right? So I didn't know that this was on a D drive. So the first thing I need to do is just to do D, and then I'm now in the D drive, and now I can do CD and then Control V again to go directly in this location. So you could go there if you know where it is. It's even easier when you just do Shift and right-click copy as path, because you can have the actual path for your folder. Now if I do that, now I am in the right folder, so I can directly do a Jupyter notebook. So I'm just going to open again. This is going to go there. And now if I do Jupyter notebook, it opens Jupyter in the browser, in the web browser, at the location I was in Anaconda. If you go back here, I was at that location where I put my folder I downloaded from GitHub. And so actually when I open it, I have what is in my folder. If I go back here, so if I go back to the root, here I have the same folders, same files. And I told you we're going to use the notebook for the local installation. So I'm going to go to local, and then we want to do image classification, so I'm going to go into classification. Now we have two notebooks for training, one for training MNIST, one for training mobile net v2, and two notebooks for running, one for MNIST and one for model net v2. Here you have the models and utils. So if I go to models, I can see what's the architecture for MNIST, and as you can see, it's extremely simple. So you take your input, then you do a layer of 32 3x3 convolutions, followed by a ReLU activation, then max pooling, then a layer of 64 3x3 convolutions with ReLU activation, second max pooling, flatten, and then dense. So it's a complete linkage between the last layer, which is made as one dimension, and the number of features, which is the number of classes. It's extremely easy to actually write the architecture of a model, of a deep learning model. And if you go to details, it's all the different functions that we need to do, everything we want to do within these different notebooks. I'm not going to go into the details. I encourage you to have a look at it if you're interested. It's simple Python. It's not that difficult to understand. And if you're motivated, you should be able to at least get some understanding out of it. You can also follow some Python classes. There are many on the internet, so you can understand how to code in Python, and then this is going to look really easy for you. I'm going to open the training MNIST. And so all the notebooks we're going to use during the workshop are organized the same way. You have these notebooks, so you have two kinds of panels. You have text panels that don't do anything, that just describe what you do in the next panel, and then a code panel with some gray shading. So if you want to run this panel, you go there, and then you come on the run icon, and it's going to run this panel. When it's running, you see you have a star here. When it's down, you have a number corresponding to the step you did. So that was the first step we actually used. So it's 1. So here, we just loaded everything we're going to need to train MNIST. Then the second panel is going to be about the parameters. So you can also run the text panel that doesn't do anything, because text panel don't do anything. And then I can run the panel, and now I'm going to define the different parameters. So first of all, training directory. So where I have my trainings, it's going to be in, I don't know, casino and normal training, where I have all of the images and the label. If I scroll down, I should be able to also see the label. So you can select the folder, and validation, it's again in adenocarcinoma normal in the validation folder. So it's a similar folder, but with less images, because we don't need that many images. And again, we have the labels here. So you can select it. So when you select a directory, that's highlighted in green. If you were to select a file, it would be in yellow-orange. Output directory is where the model is going to be saved. So by default, it's in models. Select this. And then you have a few parameters that are related to your images. So we have HNE images. These are 3-channel images. So I'm going to state it's 3 channels. Number of classes here, we have adenocarcinoma or normal. So we just have 2 classes. The imaging field is the size of your image you consider. So we saw that we have at least, at maximum, it's going to be 512 by 512 because the images for normal tissue are 512 by 512. If I select a smaller imaging field, then for each iteration, there's going to be a random cropping of my image of the size of the imaging field. So, for example, if I use 256 by 256, it's going to randomly crop 256 by 256 image patches in my images. So I'm going to keep it as it. The learning rate here is very important parameter. If it's too large, it's going to the optimization is going to diverge. If it's too small, the optimization is going to lead to underfitting. Then the number of epochs is the number of times you go through, you grow iterating across all your images. So we can also apply some data augmentation. And then you have the size of your batch, how many images you process at once. And finally, the ratio of training in validation. If you don't define validation directory, then it's going to randomly select. In that case, it would be 20% of your data in the training directory as validation. So now, as I have both training and validation directories here, I don't need to define this value. Now, I want to test several values for the learning rate. So I'm going to change. You have here a small parameter. If you change that, let's say to 4, then I'm going to have 4 sets of parameters. If I execute it, here I'm going to have first set of parameters, second set of parameters, third set of parameters, fourth set of parameters. And that's what I'm going to do right now. I select, so training, validation, in the model. I have 3 channels, 2 classes, and I'm going to use very high learning rate. Then training directory, so it's training, validation, channels, 2 classes. This time is going to be 0.01. Training. 3 channels, 2 classes, 0.0001, right? Finally, training, validation, 3 channels, 2 classes, and this time 1 minus 6. And now, if I run this panel, it's going to run, so it's going to train an MNIST model with the 4 different sets of parameters. Do this, and now I'm going to just speed up the video so you don't have to wait for the training time. It's going to take a little bit of time. All right, it's done. So as you can see, within the notebooks, you can hide most of what is in there. Right here, you see, this is the first training, so we have 560 training images and 130 validation images. We also have some information. So here it's we have a number of images, as we only have one image per batch size. So we have 516 batches. So it took 7 seconds, the first one, then 2 seconds per epoch. We have the loss, the accuracy, and then loss and accuracy for validation and value of the learning rate. So you can try to figure it out just by reading this information, or you can use a Tensorboard, which is much easier. So when you open Tensorboard, it's going to go, in that case, going to go in the log directory where we saved all the information that's used by Tensorboard. In that case, we have training and validation for 1, 2, 3, and 4. So that correspond to 4 sets of values we define. Now, I can remove them all, show the first ones, for example. Here, pretty interesting. So here we're looking at the accuracy, here at the loss. So if you remember, we want to minimize the loss, or we want to maximize the accuracy. Here, the accuracy is easy to compute because it's just the number of images, portion of images in the validation datasets for which we found the right class. And here, both the training is it's converging to 0.4964, as you can see, and it's never changing, and validation never changes. So clearly, it's just so here we see it's even worse for both training and validation that we would do it randomly if you flip a coin, and it's not converging. And it's just because, so here you have to remember that the first set of parameters we had a learning rate of 1, and clearly it's too large, and the optimization doesn't converge at all. Here, values for the loss are so large that we don't see anything. And these are extremely large values. The last information you have, when you look at these values, you can see how much time it took. So it took 3 minutes and 30 seconds. It's not that long for 100 epochs. So we can go to the next one. And probably I'm going to remove the first one because it's hiding everything for the loss here. And scale it again. So here, when we look at it, we see that, so the training is doing something pretty weird, and then just flat here, and same thing for validation. And so, clearly, when you have a validation accuracy that is not changing, that's probably because you are considering all of the images to be one class. So here we have 0.57, about 0.57, and probably we have 57% of our images of one class and 43% of the images to be the other class. And here, I guess that all the images are considered to be one class all the time. And that's why we have this score. And we see that the loss is decreasing for the training set, but clearly then doesn't change. And so here, it's not very good. It's probably still overfitting. Now let's have a look at the next one. That looks much better. The accuracy looks much better. Now we have, so here it's for a value of 0.0001. Now we can see something that makes some sense. Okay, so the training is in magenta, validation is in green. The accuracy is slowly increasing across the epochs. Validation is increasing and then decreasing. And the loss, we have something similar. It's decreasing for validation. It's plateauing earlier. What does that mean? It means that here, probably as we have some difference between validation and the training, we have some kind of overfitting. But clearly it's much better than before. So I can remove the one before, and we're just going to compare with the last set of parameters. And here, interesting, because here the performance is much worse, and the loss actually for validation is increasing. When you look at these values, it seems that we have some overfitting, but we know that here the learning rate has a low value, 1e-6, and probably here is just not converging at all. So it'd be interesting to train again with values that are more similar to this one. So here we see it's for 1e-4, so maybe 1e-5, 1e-3 to see if it's getting better. But here clearly that when we look at the curve, this is definitely the best training. Now, as we have some of the fitting, maybe we could apply some data augmentation to try to improve. We won't do it because we'll see that by using transfer learning, we can do better.